Good day, everyone. My group is assigned to discuss about subgroups, specifically cyclic subgroups, its definition and its properties. I am Christine, the first reporter, followed by Zohara Ismael, and the last will be Jasmine Gana. Subgroups, cyclic subgroups, definition and properties. Subgroups, a subset H of a group. G is a subgroup of G if H itself a group under the operation in G. Second, important points. H is a subset of G. H is a group. H and G use the same binary operation. Example: G equals open Z plus close parenthesis H equals 5Z plus close parenthesis. Third, another example. G equals Z for H equals 0, 3. H is a subset of G. H is a group. Addition, mode 4. Terminology: trivial subgroup, improper subgroup, non-trivial proper subgroup. Last one, fifth slide. Cyclic groups and subgroups. We can always construct a subset of a group G as follows. Choose any element A in G. Define A and element Z. Example is the set consisting of all powers. Thank you.
Let me introduce a notation called exponential notation. So we define this symbol a to the power of n is equal to the product of itself, where you will copy a into n times. So let's say, for example, a cubed means a times a times a. Next is a to the power of negative n. It means that the inverse of a repeated n times. For example, a to the power of negative 3 is equal to a inverse times a inverse times a inverse. And lastly, a to the power of 0. So we all know that in a law of exponent, every number that raised to 0 is equal to 1. But in a group, a to the power of 0 shall always mean the identity element. However, in a group where the operation is not multiplicative in nature, for example, if the operation is addition. If the operation is addition, we use additive. For the additive notation, we put the exponent beside the number. So NA means a plus dot plus a. This is called summand. So when I write 4a, that means a plus a plus a plus a. Next, if we have minus NA, this means the additive inverse of a repeated n times. For example, negative 5a, we will write the inverse of a negative 5 times. And 0a is 0. But let me clear that 0 here is the integer, while this 0 is the 0 as the identity element of 6. So let's move on identifying the subgroup under modulo addition. For example, identify all the subgroup of G sub 12 under modulo addition. So we all know that G sub 12 under modulo addition is a subgroup because it is satisfy all the properties of the group. First is the clause with respect of the operation. Second, it's associative. Third, there is identity element which is 0. And the last property is all the elements have inverses. To identify all the subgroup of G12, we pick up one element of G sub 12 and add it to itself several times and stop until you get the identity element which is the 0. So G sub 12 has the element of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Next, consider the group G sub 12. So G sub 12 consists of elements 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the binary operation is addition modulo 6. For example, if you want to compute 6 plus 7, 6 plus 7 is 13. But 13 mod 12 is same thing as 1. For assurance, we can make a table for J sub 12 to confirm that 6 plus 7 is 1. So let's move. Consider the cyclic subgroup of G or G sub 5. We will look for the cyclic subgroup of G sub 5. Let's start looking at the subgroup generated by element 1. So I would start 1 and added 1, that is 2. Added 1, that is 3. Add 1, that is 4. Add 1, we get 5. But 5, mod 5 is 0. So we will stop here since we already have the identity element 0. For cyclic subgroup generated by 2, we will start from 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 mod 5 is 1. 1 plus 2 is 3. Plus 2 is 5. Mod 5 is 0. For cyclic subgroup generated by 3, we will start from 3. So 3 plus 3 is 6. 6 mod 5 is 1. 1 plus 3 is 4.
4 plus 3 is 7. 7 mod 5 is 2. 2 plus 3 is 5.
But 5 mod 5 is 0. For cyclic subgroup generated by 4, we will start by 4. 4 plus 4 is 8. 8 mod 5 is 3. 3 plus 4 is 7. 7 mod 5 is 2. 2 plus 4 is 6. 6 mod 5 is 1. 1 plus 4 is 5. 5 mod 5 is 0. And for cyclic subgroup generated by 0, and for the cyclic subgroup generated by 0 is only 0. So this concludes that almost the cyclic subgroup generated the entire group of G sub 5. Only the cyclic subgroup 0 is not the generator of G sub 5. Let's move to another example. Consider the cyclic subgroup of G sub 12. We will look for the cyclic group of G sub 12. So let's say that we already performed the operation and we discovered that the generators of G sub 12 are the cyclic subgroup of 1, 5, 7, and 11.
Let's proceed to the properties of cyclic group. So the criterion for A to the power of I
is equal to A raised to J. So let G be a group and let A the element of G. If G has infinite order, then A to the power of I is equal to A raised to J, if and only if I is equal to J. If we found out that A to the power of I and A to the power of J are the same answers, but it has finite order in a different story, as we can do the operation I times and J times, as long as it divides the different I and J. Then A to the I equal A to the J. In example, let's choose 4 in Z sub 12 and find I and J such that 4 to the I is equal to 4 to the J. So let's figure out first the order of 4. So the order of 4 is 8, 4, and 0. So the order of 4 is 3. Because of a phenomenon of the statement, I minus J has to divide 3. So let's try I is equal to 3 and J is equal to 2. So we have 4 to the power of 3 is equal to 0, but 4 to the power of 2 is equal to 8. In this case, I and J are not equal. So next, let's try I is equal to 2 and J is equal to 1. And we have 4 to the power of 2 is equal to 8, but 4 to the power of 1 is equal to 4. Therefore, the I and J was not equal to each other. Let's try the third one. I is equal to 3 and J is equal to 0. So we have 4 to the power of 3 is equal to 0. And 4 to the power of 0 is equal to 0. Therefore, the only possibilities are 3 and 0, since the value of I and J are equal. Let's now move on to another properties of cyclic group, which is the theorem every cyclic group is abelian. Abelian group is also called as commutative group, in which the result of applying the group operation to two group elements does not depend on the order in which they are written. So let's have the proof. Let G be a cyclic group generated by G. Let A be P elements of G. In that case, we want to show that AB is equal to BA. So now we have A is equal to G to the power of M and V is equal to G to the power of N for some integers A and V. So AB equal G to the power of M and G to the power of N is equal to G to the power of M plus N, and BA equal to G to the power of N and G to the power of M is equal to G to the power of N plus M. But M plus N is equal to N plus M, which is the addition of integers is commutative rather. So therefore, AV is equal to BA. For examples, for number 1, we have Z and plus is a cyclic group because G is equal to the element of 1. If the quotient by the center is cyclic, then the group is abelian. Second, we have NA made of n element of Z and plus is a cyclic group where A is n fixed element of Z. Last, we have Z sub n and plus is a cyclic group because Z sub n is equal to the generated element 1. that's the end of our discussion. I hope or we hope that you've learned from us. Thank you and God bless us all.